In this lesson, we're going to take a look at systems of objects, which means we're going to be dealing with more than one object, and those two things are going to be connected somehow. And we want to examine the forces on both of them and apply Newton's laws to both of them. Now, in lab, we looked at the case where we had a cart, and we'll call this M1, that was being pulled along by a hanging mass connected by a string that hung over the side, and we'll call this M2. So we have M1, which is resting on a track, and we have M2, which is hanging off of the string and is allowed to fall. Now, what forces act on each one of these? We're going to analyze this problem in two ways. We're going to analyze this one object at a time, and then we're going to analyze it as a whole system. So first, let's look at M1. M1 has a few forces acting on it. It's got the force due to gravity. I'm going to call this Fg1 because it's on object 1, and it's got the normal force Fn1. There's also tension in the string. I'm going to call that Ft1. Okay? Now, generally speaking, it's a good idea to assign positive and negative directions, and to the right is generally considered positive, and down is generally considered negative. Now, when we have multiple dimensions like this, we're going to have to pay extra special attention to what's happening with those things. And the other thing we want to do is label the forces on object 2. So on mass 2 we have Fg2, and this is why those subscripts are important. Fg1 and Fg2 are different because it's a force due to gravity acting on different masses. And over here we also have Ft2. And again, those two forces, while they might be equal in magnitude, because Newton's third law, right, it's a string, so we pull on one side of the string, equal on opposite side on the other side of the string, those might be equal in magnitude, but they might be opposite in direction. So we've got to pay attention to that. Right? So we've got our forces labeled on each object, Ft2, Fg2, Ft1, Fn1, Fg1. Now there might be a frictional force on this cart. We can ignore it since it's so small. If it was there, we would just have to keep track of it when we're applying Newton's laws to this thing. So let's go ahead and actually do that. Let's apply Newton's laws to each object. So object 1 is this cart, and all I want to do is focus on the forces acting on that cart. Now I'm going to say net force, and I'm only going to pay attention to the x direction, x being horizontal, because the normal force and gravity are going to balance and cancel each other out. So the net force in the x direction is given by Ft1, and that's going to equal m1 times a1, where that's the mass of object 1 times the acceleration of object 1. Now if we look at the second object, that's this one, we have, again, Newton's second law. So this is the net force, and this one's y, because this is the vertical direction, the net force in y, and I went ahead and have it assigned down as a negative direction, is equal to Ft2 plus Fg2, and this is equal to m2 a2. Okay? So we have two equations, and what we're trying to do is determine the acceleration of this system in terms of those two masses, and gravity, of course, because gravity is what's causing this acceleration. So it looks like we're going to have some algebra to do, because we don't necessarily know Ft. We do know m, but we don't know a. So let's take a look at how we can simplify these things. Well, the first thing that we should recognize is that A1 and A2 are going to be the same magnitude because these two things are connected by a string. But the way I set up my frame of reference, the way I set up my positive directions, A1 is going to be accelerating to the right, which is positive, and A2 is going to be accelerating down, which is negative. So I'm going to go ahead and I'm going to write that. I do know that A1 is equal in size but opposite in direction of A2. The same thing is true of the tension, right? Tension 1 is to the right. It's a positive tension. Tension 2, it's positive as well. It's up. So actually I have Ft1 is equal to Ft2 because both of those would, they're equal and opposite Newton's third law, but because positive is up and positive is right, they have equal magnitudes and the same direction. We don't have that opposite thing to deal with, which means we can actually start making some substitutions. There's not a lot I can do with this equation to simplify it, so I'm going to leave it there for now. This equation, there is some stuff I can do to simplify that. So first thing I'm going to do is, since I have a T1 here and a T2 there, that's two unknowns, I don't want to have to mess with that. I'm going to go ahead and make the substitution right there. So I'm going to replace Ft2 with Ft1. Ft1 plus Fg2. Now let's think about that. That's the force due to gravity. Gravity's pulling down and it's on that thing. So I can say plus m2 times negative g, where g is the acceleration due to gravity, right? And it's negative because it's pulling down, is equal to, and here I have m2, a2. This is an a1, and so since I don't want to have multiple variables running around if I can help it, I'm just going to go with m2, and I can replace a2 with negative a1. Negative a1. So now let's look at what I actually have. I have this equation, which I'm going to rewrite, and since Ft1 is equal to Ft2, I'm just going to go with Ft. So I have the tension force is equal to m1a1. But I also have that the tension force minus m2g, right? I just simplified that, is equal to the opposite of m2a. And since I've replaced all my a's with a1, I'm going to go ahead and just write a again. Well, now I'll write a1. Okay, so these are two equations, and now I can substitute one equation into the other equation to eliminate an unknown, right? I don't know Ft, but it's in both of these equations, so I can make that substitution. So I'm going to replace Ft with m1, a1, minus m2g equals negative m2, a1. Now I'm trying to solve for a, so I'm going to collect my like terms. I'm going to go ahead and add this to the left side and add the m2g over, so I get m1 a1 plus m2 a1 equals m2g. Okay. Now I'm going to factor out that a1 times m1 plus m2 equals m2g, and now I'm going to divide both sides by m1 plus m2. So a1 equals m2g divided by m1 plus m2. This equation right here tells me the acceleration of this whole system, a1, is equal to m2g divided by m1 plus m2. Now let's look at that strictly in terms of Newton's second law, which says acceleration is equal to net force divided by mass. Well, the net force is the unbalanced force that makes this thing actually accelerate. And if we look back at the whole system, it's worth noting that this tension force right here and this tension force right here, those are actually pulling against each other. And if we had looked at the whole system, those forces would be internal to the system and would not actually cause accelerations. They're not external to the system, they're part of the system. Remember, a force is caused by an agent that acts on an object. Well, if this system is my object, there's no agent to cause those forces. So that's what I mean when I say they're internal forces and they can't cause acceleration. The normal force and gravity over here balanced, which means the only force that didn't have anything balancing it is Fg2. Well, over here, my net force corresponds to m2g because that's the only unbalanced force. Now, that force had to accelerate two things. It not only accelerated the mass of the hanging mass, but it accelerated the mass of the cart as well. And so we got our total mass that's accelerating is m1 plus m2. So really, we did a whole bunch of algebra, and we substituted one equation into another, and all we have is Newton's second law. Net force equals mass times acceleration. And so we found our mass is the total mass that's being accelerated, and our net force is the only unbalanced force that is acting to accelerate the object. Okay. Now let's look at this again if we look at it as a system instead of two objects connected by a string. So now let's look at this again, but this time instead of looking at two separate objects with forces acting on both of them, we're going to take a look at the system of objects. And so that means I'm going to go ahead and enclose this thing so we understand that forces that can actually cause acceleration have to come from outside that system. Now, as far as I can tell, there's three forces that are coming from outside this system. There's this force right here, which is m2g, mass, the force due to gravity acting on mass 2, and there's this force right here, m1g, and there's this force right here, Fn. Those forces right there still balance, so those sum to 0, which means the only unbalanced force is m2g. Now, the trick on this problem is going to be assigning a positive direction because we have horizontal changing into vertical. And so when we look at this whole system, I'm going to say let's let this way be positive. That means I let clockwise be a positive direction for this system. Now, once I do that, then it's just a matter of applying Newton's second law. Newton's second law says net force equals mass times acceleration. The only unbalanced force, the only force that I have to worry about is m2g, and that's equal to mass. Well, the mass that is being accelerated is the whole system, m1 plus m2 times a. And so we can see right away the acceleration is equal to m2g divided by m1 plus m2. That's exactly the same result we got before when we looked at two different objects and the forces acting on them individually. This whole system, the system approach, simplifies the math. You just have to be careful with your directions. And what I mean by that is if we had had a frictional force acting on this system, say there's a frictional force on the cart, Fk, we would need to account for that. And it would be a negative force that we would have to deal with. And so our net force here would, instead of just be m2g, our net force, if we were looking at this with friction, we would have m2g minus Fk equals m1 plus m2a. And so we subtracted that because the value of that force would be negative compared to the value of our m2g force.